Hello again, Physics 30s. In today's lesson, we are going to continue forward in the nuclear physics unit of study. In the last lesson, I did introduce you to both what a nuclear reaction is and how to write a nuclear equation, although the reactions we looked at were not really specific. So today we're going to get a little bit more specific in the types of reactions that are going to be studied. The learning outcome is to compare and contrast the characteristics of nuclear fission and of nuclear fusion. Before we do that, though, we'll just talk about more of like a general type of nuclear reaction, which I've identified as induced nuclear transmutation. This involves the disintegration of a stable nucleus by striking it with another nucleus. So we could have two nuclei collide, which could result in a nuclear reaction with different types of elements. I could also take an atomic or a subatomic particle, like a neutron, and fire it at a stable nucleus, and that could also induce a nuclear reaction. Or you possibly could just take a gamma ray photon and fire it at a stable nucleus, and it could once again result in a nuclear reaction where you get a new type of atom. Induced nuclear transmutation can produce transuranium elements. Transuranium elements are ones that do not naturally occur, which means when I say do not naturally occur, it means you can't take a shovel and dig it up and just find it, or you can't find it in the air. They can only be produced artificially in a lab type setting. So the three examples I gave were neptunium. I think Pu is, I want to say plutonium, but I feel like that's wrong. So let's just quickly check. Pu is it is plutonium. Okay, so I was right. And Am is americanium. Okay, so an example of this would be you have uranium-238 and you fire a neutron at it, so it's a subatomic particle, and that results in you getting uranium-239 and a gamma ray photon. Now, so far, I haven't produced anything new. I'm just going from uranium to uranium, but it turns out that uranium-239 is not very stable. So what uranium-239 will do is it'll spontaneously decay. And it spontaneously decays into neptunium-239. So that's my new element. You get an electron emitted in the process and another gamma ray photon. But I believe neptunium is also not very stable. So neptunium will actually spontaneously decay into plutonium-239. And also you would get an electron and a gamma ray. So yeah, like the neptunium, plutonium, they're elements that do not naturally occur. They seem to come from like a variation of uranium, which I suppose is also why they're called a transuranium element. But that's like one kind of general type of reaction. Again, I got the whole process started by just firing a neutron at the uranium. We're going to come back to this in a moment because firing a neutron is going to be a way to induce another kind of nuclear reaction. But our main focus today is on nuclear fusion and nuclear fission. Nuclear fusion involves taking a couple of smaller elements and forcing them together to give you a larger one. So in a nutshell, what you're doing is you're taking, let's just write down a little reaction here. So you are taking, sorry, I have my tablet upside down. Okay, so you are taking one small element, X, you're combining it with element Y, and they're fusing together to give you just one new type of element, which is we're going to call Z. The problem is this is really hard to do because what you're doing is you're taking a bunch of protons and you're forcing it together in an even smaller area. So it turns out that this is actually something we can't do. Like, I don't believe what we can do controlled nuclear fusion reactions on Earth at this point. However, if you had an area where you had really high temperatures and large pressures, you could bring these two nuclei together. So again, like, these guys don't want to come together because they have like positive charges in their nuclei. So to get it together, it's going to require really high temperatures, really high pressures. So where does this occur? Well, the sun. Okay, so the sun has a really, really high temperature, and also like the gravitational pressure, because of like the sun pulling everything towards the center, is really, really high because the sun's mass is so large. And again, you need these high temperatures and pressures because you have to overcome the electrostatic force of repulsion. Okay, it's very tough to bring charged objects and bring them closer and closer together, especially within like small distances inside of the nucleus. However, once you do this, you can bring like your charged particles close enough together to form your one daughter isotope. There's another fundamental force, which we'll talk about a little bit later on, which is referred to as the strong nuclear force. The strong nuclear force, you can kind of think of it as like the glue that like holds the nucleus together. And the strong nuclear force is exceptionally powerful, but only powerful over a really tiny distance. So you have to put a tremendous amount of work into getting nucleus X and nucleus Y together. But once you can get it together, again, you need this high temperature and pressure to do it, then my strong nuclear force can take over and hold the thing together. And again, we'll talk more about the strong nuclear force later. So here's an example of nuclear fusion from hydrogen. So we have hydrogen 2, and hydrogen 2 produces helium 3. You get a neutron in that reaction, and you also get a large amount of energy produced. So again, the idea right here is you're taking like one element and you're combining it with another one to get like a larger isotope or a larger atom. But even this, and hydrogen just has one proton and one proton. Even to bring a proton and a proton together to get helium is exceptionally difficult to do. So you can imagine how much more difficult this would be if you tried to combine nuclei that had even more protons. Yeah, whatever. It's just a picture showing what goes on here. We'll talk more about like what this subatomic particle and neutrino is in the next lesson. Okay, now we're going to spend a lot more time talking about nuclear fission because this is something we actually can do in a controlled fashion. So nuclear fusion is you take two and bring them together to get one. Nuclear fission is going to be the opposite. So you're going to take a larger atom and you're going to split it into a couple of smaller ones. However, in order to do this, to take a large nucleus and to split it into a couple of smaller nuclei, you need to fire a neutron at the larger nucleus to kind of induce this nuclear reaction. So the example I have here is this is a nuclear fission of uranium-235. And in the CANDU nuclear reactor, I feel like that's somewhere in like Ontario or Quebec, but I'm probably wrong when I say that. So the idea is you have a neutron, and you fire this neutron at a uranium-235 nucleus, and it causes the nucleus to split into one part here and a second part over there. Okay, so you're taking one and you're splitting it into a couple of pieces. So this reaction is uranium-235 plus a neutron to induce the reaction would give you barium-141, krypton-92, 3 neutrons, and a large amount of energy. I do want to point out, by the way, that anytime you have a whole number coefficient in front of like a quantity in a nuclear reaction, this whole number coefficient needs to be multiplied both by the top number and it needs to be multiplied by the bottom number. So by doing that, that would make sure that my conservation of nucleons on the top is balanced and the conservation of charge on the bottom is balanced. Okay, now, this isn't the easiest thing to do. So again, we need to fire a neutron to induce this reaction. If you fire a neutron at the right energy level, what it'll do is that neutron will enter the large nucleus. It'll cause it to oscillate uncontrollably. So that this neutron enters in here. Then it causes this nucleus to start oscillating up and down, and eventually it splits. And splits into those two parts that I've identified in the previous slide, which I think was like barium and krypton. However, if your incoming neutron is too energetic, it actually will just, so let's erase this here. It'll actually just zip right through. Okay, it won't do anything at all. Okay, so too energetic is not going to be good. And also, if it's too slow, what would happen is instead of like just zipping straight through, it would actually just bounce back. So your neutron would just hit this larger nucleus and then just get sent back in the reverse direction. So there's a specific energy level that we need to fire it at that is going to cause this to split. I don't know what the exact numerical value is, but there is like kind of a value that's going to cause this to occur properly. But the interesting thing about nuclear fission is it leads to something that's called a chain reaction. So what do you need for nuclear fission to occur? Well, you need a neutron. However, in the process of nuclear fission, you also emit a few neutrons as well. So what we can do is we can take, so in a sense what's happening is like one of the reactants we need is a neutron, but in the process we're also, in the products, we're getting some more neutrons, which we need to make the reaction occur. So if we take those neutrons that are produced and we direct them towards other uranium-235 nuclei, then you can continue the fission reaction. Okay, here's what I mean by this. So let's say we take our single neutron and we just fire it at uranium-235. So that's going to cause it to split into my two parts. So it splits into the krypton and it splits into the baryon. Now, on average, you get about 1, 2, 3 neutrons. If we take those neutrons and then we direct them towards other uranium nuclei, then we can cause those uranium nuclei to split. Okay, so then it splits into, here's part 1, here's part 2 for this one, part 1, part 2, part 1, part 2. And then for each of these reactions, you're once again getting, on average, 1, 2, 3 nuclei. And then if we can take these and just direct these neutrons towards other uranium-235, we can make the reaction continue to occur. So the reaction is self-propagating because in the process of nuclear fission, I get a neutron, and a neutron is the thing that I need for the reaction to actually occur. So one of the reactants I'm getting from the products in the reaction. Now, this can get out of control very, very quickly. So you can see here that like, I think in the first situation, I'm just like reacting one neutron with a single uranium atom. And then the second time I'm reacting it with 3 uranium. And the next time we could actually react it with 9. The next time it'd be 27, 81, etc. So yeah, if you don't know what you're doing, this reaction can get out of control very, very quickly, where you're actually producing way too much energy, which would lead to a nuclear meltdown, which is something that has happened in like a few nuclear power plants. Now, although we can do nuclear fission, and it does produce, like a tremendous amount of energy, there are a lot of problems that are associated with it. Okay, the first problem is that uranium-235 is rare. Now, we actually have talked a little bit about this before. So back in the magnetic forces and fields, we discussed the mass spectrometer. And the point of a mass spectrometer was we can take like a sample of uranium that has a bunch of different isotopes of uranium, and we can actually separate it according to mass, because the the isotope uranium we want is 235, okay, because 235 is the one that'll undergo nuclear fission. I believe other isotopes of uranium do not. I think there's one other one that might, but I'm not quite sure which isotope it is. But most other isotopes of uranium will not undergo nuclear fission. Okay, so it's rare. So of all of our different uranium isotopes, less than 1%, so 0.71% of all uranium is the 235, the kind of uranium that can actually undergo nuclear fission. Okay, so it's tough to find. And then, then once you do find some uranium, you got to use a mass spectrometer to separate and get the uranium that you want. And as I already identified, other isotopes of uranium will not produce a chain reaction. Again, there might be one other one, but don't quote me on that. 2, the products in nuclear fission are very, very radioactive. Okay, like they're not good elements to get. So if we go back to this reaction, we're getting in the nuclear fission, we're getting this krypton and this barium. Okay, so this isn't the point. We're not trying to get krypton and barium here. What we're trying to do is we're trying to get energy out of this. Like, that's the important thing, to get energy out of the actual reaction. But in the process, we get these like byproducts, the krypton and uranium, which are radioactive. So they need to be stored because you have all this nuclear waste. So this isn't the greatest energy source because it's non-renewable. Okay, you can't take that radioactive waste and easily store it. Okay, third one is that reactors can be subjected to mechanical or human errors. Okay, and if the reactor is not properly maintained, or if the equipment is faulty, can lead to a nuclear reaction. So the one example I can think of is Chernobyl, and I believe in Chernobyl, like there's a couple different theories in terms of like why that nuclear power plant had like a meltdown. So one of them, I believe, was again that there was just human error. So whoever was operating the power plant just didn't really, just that they didn't know what they were doing, but they made some kind of error. Other one is just mechanical in terms of like just whatever like materials were like used in the actual plant were faulty, which also led to the reaction. Again, I think I'm not sure if there's like conclusive evidence on like which one was the result of the meltdown, or if it was even a combination of both. I did want to point out, though, that it's unfortunate we cannot do nuclear fusion, because nuclear fusion would be much safer. So in nuclear fusion, you're just taking a couple of protons and combining it together to get helium and a ton of energy. We're not really getting any harmful radioactive waste in that process. So that might be another motivation for us to eventually try to get nuclear fusion in a controlled fashion, is that it would be environmentally a lot more sound in comparison to nuclear fission, which does have a lot of negative environmental consequences. Now, the point of nuclear fission and nuclear fusion is that we want to get energy. We want an energy source. Now, to calculate how much energy is released in a nuclear reaction, we can use the following equation. Delta E is equal to delta MC squared. Now, in this situation, delta M is going to represent something a little bit different. If you take the mass of your products and you take the mass of your reactants and subtract them, you're going to get a mass defect. It doesn't matter whether it's nuclear fission or it's nuclear fusion. In either of those processes, you're going to get a mass defect, which makes it seem like there is some mass that's once again missing. So if there's some mass that's missing, I believe that means that your reactants would have a larger mass than your products. Okay, so we can say like your sigma MP would be less than the mass of all my reactants. Okay, so why am I losing some of my mass? Well, some of that mass is being converted into energy. How do you determine how much energy it's being produced? Use this equation. So we can figure out the mass defects between your product and reactants mass. multiply by that conversion factor, c squared, and that'll enable us to calculate the amount of energy that's released. And again, it doesn't matter whether it's nuclear fission or fusion, you have a mass defect, and that's a reason why we can produce a lot of energy in either of those reactions. Okay, let's do one simple example first, and we'll get into a more complicated calculation problem. So it says an alpha particle strikes an aluminum-27 nucleus. As a result, a new nucleus and a neutron are produced. Identify the daughter nucleus produced. All right, this one is not an example of nuclear fission or fusion. This is an example of induced nuclear transmutation. So we could have actually done this one in the last lesson. So an alpha particle is 4, 2, He. And we're reacting it with aluminum, 27. That's the nucleon number, so that goes at the top. And aluminum has an atomic number that is 13. All right, look at that one a lot faster than I did the plutonium. Okay, it tells me that as a result, you get a neutron. So a neutron is 1, 0, N. And you also produce some kind of daughter nucleus. So a daughter nucleus is going to have a nucleon number we need to calculate. It's going to have a charge number we need to calculate. And it's also going to have, well, we're going to try to figure out what the element is. Okay, so in this situation, let's pick a different color. Okay, so let's try to balance the top numbers first. So again, the sum of the numbers on the top on each side has to be the same. So 4 plus 27 would be, this would be a combined number of 31. So 4 plus 27 is 31. This side of the equation also has to add up to 31. So what's 1 plus 30 would then be 31. So this number right here needs to be the 30. Okay, it looks kind of messy with the box there, so we just get rid of it. Okay. Okay, so 30 plus 1 is 31, 27 plus 4 is 31. So my nucleons is balanced. Bottom has to add up to 15 on both sides of the equation. So this number would just then be 15. Okay, which element on the periodic table has an atomic number of 15? I believe that is phosphorus, P. So that's my nuclear equation. And then what's the daughter isotope produced? We should just write down the name of it. So that's going to be phosphorus. Phosphorus. And then hyphen, and then after the hyphen is the nucleon number, so that would be phosphorus 30. Second example. This one deals a bit more with like calculating how much energy is emitted in one of these nuclear reactions. Okay, so given the following reaction, calculate the energy released from the fission of one atom of uranium-235. It gives me the mass of all my different isotopes, and it also shows me what the nuclear reaction is. All right, so what we need to do is to calculate the energy, we need the mass defect. To get the mass defect, I need to know what the sum of the mass of the products are and the sum of the mass of the reactants. Okay, so let's get the sum of the mass of the reactant first. So this would be sigma MR, which I'll use for sum of the mass of the reactants. Okay, so that'd be equal to the mass of uranium-235, which it tells me its actual mass is 234.9934 atomic mass units, plus the mass of a neutron. And we're going to have to go back to that previous lesson to get the mass of a neutron in atomic mass units, but I believe it is 1.008665. Atomic mass units. Okay, so add those two up, and then that would give me, so we'd have 234.9934 plus 1.008665. So we'd then get 236.002065 atomic mass units. Get the sum of the mass of the products. So we use sigma MP to represent that. Okay, so the products, barium-141 has an actual mass of 140.88340 atomic mass units, plus the mass of krypton, the actual mass, 91.90601 atomic mass units. By the way, these numbers are the actual masses, not the theoretical ones. So they're actually already accounting for that binding energy to hold them together. Okay, and then plus we have 3 neutrons. So 3 multiplied by 1.008665 atomic mass units. Okay, so let's calculate that. So 140.88340 plus 91.90601 plus 3 times 1.008665. And that gives me 235.81545. Okay, so we've had a mass decrease, which is exactly what should happen in whether it's fusion or fission. Okay, because the mass defect is going to give us our energy. All right, let's get the mass defect now. So that's delta M. So delta M is the sum of the mass of the products. Subtract the sum of the mass of the reactants. So that would be 235.81545 atomic mass units. Subtract 236.002065 atomic mass units. And that's going to give me a delta M that would be equal to, so let's plug this in, 235.815405 minus 236.002065 would give you small mass defect. So you have negative. It's negative because you're losing mass, 0.18666 atomic mass units. Okay, we need to convert this into kilograms. So I know that in 1 atomic mass unit, I have 1.66 times 10 to the negative 27 kilograms in 1 atomic mass unit. So this would give me delta M. Okay, now we're going to go to 3 significant digits because we're using that value off the formula sheet. So times 1.66, second exponent, negative 27. Actually, no, let's keep some digits here just because this is not part of the final answer yet. So negative 3.098556 times 10 to the negative 28 kilograms. All right, that is my mass defect. Now, I need to calculate the amount of energy released. Now we're going to use Einstein's equation, the mass energy equivalence equation. So delta E is equal to delta MC squared. Just plug the numbers in. So that mass we got was negative 3.098556 times 10 to the negative 28 kilograms multiplied by the speed of light squared against our conversion factor, 3.00 times 10 to the 8 meters per second all squared. Okay, this is going to give me this energy difference, which is the amount of energy that's going to be released. As we don't really have to worry about the negative number. If you want to drop it, you could. But anyways, let's just include it for now. So if I include this, let's go to let's multiply by this. So times 3 second exponent 8 squared, I get a value that is 2.788704 times 10 to the negative 11. Now this is in joules. We're going kilograms times meters squared per second squared. All right, let's put this into mega electron volts. It seems to be like the most convenient unit for expressing these energies. So I know in 1 mega electron volt, there is 1.60 times 10 to the negative 13 joules. Then this would give me the amount of energy released in this fission reaction, and divide by 1.6, 10 to the negative 13, and I get 174 mega electron volts. Again, it's not a huge deal that it's not a huge deal if you write the negative sign down or not. I suppose the way I would interpret the negative here is just that energy is being released to your environment or to the surroundings. Okay, so that's it for this lesson on nuclear reactions. You can complete the assignment called nuclear reactions, and then in the next lesson, we're going to talk about another type of, another category of nuclear reactions dealing with radioactive decay. And I'll talk to you in that lesson.